So one housekeeping thing to talk about today. March 8th is your Chapter 7 test. Okay? So anything and everything needs to be, from Chapter 6, needs to be made up before March 8th. Okay? So there's 2 days in there that are ACT days that we won't have anything going on because we lose the morning classes. Actually, most of the afternoon classes too for juniors. So if you have something that seniors, if you've got something that you want to make up, those would be the days too that you could get that stuff done. Okay. So identify the values of x that makes each function undefined. Did anybody come up with an answer for number 1? What you got, Ben?
I was thinking
12 would make it undefined. Anybody agree with 12? Okay, what about number 2? Anybody come up with an answer for number 2? What you got, Kevin? 2? X equals 2? Okay. What about number 3? Joe?
I said 2 also.
Okay. Any other guesses? And -3 for number 3? Huh? Sure. 0. Okay. So, how do we do this? If I'm looking for stuff that makes it undefined, I would probably want to read the hint, right? Okay. Remember that division by 0 makes an expression undefined. So in this first equation, I would set 4x equal to 0, and I would solve for x, because then my function is undefined, because the denominator would be 0. Divide both sides by 4, x equals 0 for that one. Okay? In number 2, I take the denominator of my function. Again, we're just looking at the denominator because dividing by 0 is what makes it undefined. So I'd say x minus 2 equals 0. Add 2 to both sides gives me x equals 2. Number 3 is a little trickier. Okay. Still looking just at my denominator, and I'd set that equal to 0. And then I'd set each of those parts equal to 0 because of the 0 product property. Oops. And then I'd get x equals 2 and x equals -3 there. Okay. Denominators, where the denominator is 0, that's where my function is undefined. Okay? So the very first rule, what we're dealing with in this unit is we're dealing with something called rational functions. Okay? These were 3 examples of rational functions. Okay? So the first rule that we have in terms of rational functions So the first rule of rational functions is the denominator cannot equal 0. Yes, you should write that down. Okay? Because from every problem from now at least until spring break, the first thing that you're going to determine is when is that function undefined. And you're going to do that by setting the denominator equal to 0 and solving it. Okay? It's rule number 1 of rational functions. Okay? Your denominator cannot equal 0. Okay? So, from previous math courses, the reciprocal of a number is 1 over that number. For example, the reciprocal of 5 is 1/5. The reciprocal of 17 is 1 over 17. Okay? We can do that for decimals too. The reciprocal of 1/2, 0.5, is 1 over 0.5, but we don't like to mix decimals with fractions, so 1 over 1/2 is just 2. Throughout this course, you have studied many connections between polynomial functions and real numbers. Does it follow, then, that a polynomial function would also have a reciprocal? Meaning, if I take a linear function, let's say, would that linear function then have a reciprocal? And that's what that question is asking. Is the reciprocal also a polynomial? Is it a function? How would the graph of the values compare to the original function? Okay? So we're going to look at two functions here today, and then we're going to determine that. But first off, I would like to take a brief second here to talk about this, is it a function thing? Okay? What are two ways to determine if it is a function, if something is a function? Max?
Says f of x.
That's just function notation. Okay? That's just defining something as with a variable of x. So that's usually one, and sometimes that works, but that's not a true way to determine if it is truly a function. Okay? What Max said, for those of you that didn't hear, is if we have function notation, like g of x here, that's function notation. Okay? F of x here, that's function notation. Okay? What are two other ways to determine if it's a function or not? KG. So, what would I be looking for if I say every input has to have an output?
X and a y value.
Keep going. Expand on that.
Oh, there's always an x and then a number that doesn't have a variable on it.
Keep expanding on it. Keep expanding on it.
They're in order.
Keep expanding, because it can be in any order. So what does that mean? What am I looking for? Where would I be looking for that? And then what would I be looking for? All right, what do we come up with?
Has a slope.
That only works if it's linear.
Well, I was just remembering how it can't be a circle, right? Because you can't have two x values.
So what does that mean? You're there. You're like on the outskirts of Stevens Point, and your destination is UWSP. You know what I mean? Okay? You're right there. What does that mean? What does that look like?
X and y values have to be equal.
X and Y values do not have to be equal.
No, not equal. They have to be. There has to be the same amount of each.
Okay. But that doesn't that works for non-functions too. Nope. You guys have done it before. You've done both of these tests before.
It's got to have an equal sign.
What kind of tests can we run?
Should we put 0 in for x?
That's only going to give us 1 point though. That's only going to give us the y-intercept.
We can get
That's what we do to find the y-intercept. We put in 0 for x.
we can get our vertex.
No, you're thinking too narrow. Okay, I'm talking for any function here. Okay, for any function, what we've learned works.
Substitutions.
No,
Factoring.
what you got?
Can't have repeating points.
Can't have repeating
Like
x values. Yes. Okay. So in a table. Oops. Now I got to go back to this. In a table, no repeat x values. That's one test. What's the other test for a function? Not a function. The vertical line test. Whoa, things are just a moving here now. Get rid of that. We'll just start over again. Okay? And where would I look for that, Kevin? On a graph. Okay? So I take a vertical line and I do what with it on my graph? What do I do with that vertical line on my graph? You guys have done them. You've done them in this class.
Put it in the middle.
Okay? Then what? Nope. What do I do with the vertical line? And then do what with it? So how do I do that? I move my vertical line across the graph, right? Okay? I take my vertical line and I slide it all the way across my graph. And I might even do it a couple of times, like a windshield wiper. Okay? Alright? Back and forth, keeping that line vertical. And then what, Kevin?
And see if there is 2 points on this.
If my graph touches the vertical line twice, it's not a function. Okay? If it only touches once, it is a function. Okay? Now, what I'd like you and your shoulder partner to do is I would like you to complete page 2. Spot check, that's what your table should look like.
Sweet.
Okay? Now graph it. Spot check, that's what f of x should look like. I know, but g of x is 1 over f of x, right? Okay, so that's what f of x looks like, correct? Okay, alright. Now all you got to do is graph g of x. That's what g of x looks like. Okay. Question number 1 says, or this is part A, complete the tables, plot the points, draw a smooth curve for g of x. Did that. Part B says, describe the graph of g of x. Okay. First off, f of x is what? What was f of x? It was a line. It was a linear function. Okay. Is g of x a linear function?
No.
No. G of x is defined as 1 over f of x. Right? So even with the reciprocal of a linear function is not linear. Okay? What else do you see about it? There's 2 what?
Two symmetric. Yeah,
There's 2 separate curves. Okay, I like that. Are they connected? No, they are not connected. They are totally separate. Okay? They're what?
Symmetrical.
What are they symmetrical about?
They flip over onto each other.
But so that means that they're symmetrical about a certain point.
About 0, 0.
About the origin. Yep, they're symmetrical. It's symmetrical about the origin. It's reflected through the origin. Right? Okay? Anything else that we notice about g of x? All very good observations that we should be writing down. Okay? From that now that you have the picture of g of x, now you should be able to finish off the rest of that page. Go. So, end behavior is a concept that we've talked about already in this class. It's what our graph is doing when x is negative infinity, way over on the left side of the graph, and when x is positive infinity, way over on the right side of the graph. So that's what end behavior is talking about. It's talking about the left and the right sides of our graph. Okay? It's talking about the left and the right sides. So, as x goes to positive infinity, is that the left side or the right side? That's the right side. So if I were to continue, if I were to magically expand this TV all the way to the door, what would that green function be doing on this right side? If my green function was heading towards positive infinity, somewhere in here then it would take a turn and it would go shooting up. Is it going to do that?
No, it's going to keep going straight.
It's going to keep going straight, okay? And get closer and closer and closer to what?
0.
To 0. Is it going to get closer and closer to 0 from above or from below? On the left side, or excuse me, on the right side. Above. So we write that as 0 with a plus sign in the exponent. Okay? What that says is, that says 0 from above. It's getting closer and closer to 0 from the positive side. Because I'm taking 1 and I'm dividing it by a positive bigger and bigger and bigger number. Never getting to 0, but getting closer and closer and closer to 0. Okay? Now, going the other way. Now if I could expand this TV all the way over here to this wall, what's that function doing? It's going up to 0. Will it ever get there? No. So it's going to 0 from below, right? So 0 from below, we put a 0, and then we put a negative sign up in the exponent. This is not the same as saying negative 0. You put that negative sign up in front, it means something totally different. Okay? In the exponent says 0 from below.
Because it's an outline. Is it because it's an outline?
No. No. Let's jump down to, because that'll explain what we're talking about too. Let's jump down to this G. Will the graph ever intersect the line y equals 0? Okay? Will my function ever have a value that is 0? Is my question. Okay? Now, let's do a little fractional logic here. If I've got a fraction, a over b, tell me the only case that makes that fraction equal to 0. Joe?
A equals 0.
A equals 0. Okay. What happens if b is equal to 0? Undefined. Okay. But if a is 0, that fraction is equal to 0. Okay. My function g of x is equal to 1 over x, correct? What's the numerator of my function? 1. Can 1 ever be 0? Is really what this question is asking. Can the number 1 ever be the number 0? No. So the answer to this is no. And what we get then is something called a horizontal asymptote. Okay? Write this down. A horizontal asymptote is the line that my rational function approaches at the infinities. Okay? It's a line that the rational function approaches at x equals positive infinity and x equals negative infinity.
Doesn't that mean you just have an x value and no y? Wouldn't that be a horizontal asymptote too?
That the rational function approaches at x equals infinity and x equals negative infinity. Okay? We put those on the graph as dashed lines. Now we'll go Navy. Okay. So there should be a dashed line right there because my function is approaching that horizontal asymptote, but it will never get there. Okay. Now, let's go back to D. Describe the behavior of g of x as x approaches 0 from the left. So here I am, I'm walking along my rational function. I'm coming in from the left. Okay? I'm coming in from the left. Let me go a little different shade of green here. I'm coming in from the left. Okay? I'm getting closer to 0. And what is my function doing? As I get closer and closer and closer to 0. It's going to negative infinity. Now, side note, this here means as x approaches whatever number it is from the left. Okay? When it's attached, when we put that positive or negative sign in the exponent and it's for an x value, we're talking left and right. Up here in the blue, that was a y value, so that's why it was above or below. Okay? E. Describe what f of x is, or excuse me, what g of x is doing as we approach x from the right. So now I'm coming in along here. I'm getting closer and closer to 0 from the right. And what's happening to my function? I'm going to positive infinity. Okay. My question is, now, let's skip down to H. Will the graph ever intersect the line x equals 0? Why not, Max?
Because the horizontal asymptote.
No, y equals 0 was the horizontal asymptote. Now I'm looking at x equals 0. Why not? Why? Because then we're dividing by 0, right? Okay. So this one is no, because the function is undefined. Okay. Places where my function is undefined give me vertical asymptotes. Okay. Vertical asymptotes are of the form x equals some number. It's the spots that won't let my function work, like you were doing in the warm-ups. Okay? If I go back to the warm-up problems, number 1's function right here has a vertical asymptote at x equals 0 because the function doesn't exist if you plug in 0. Number 2 has a vertical asymptote at x equals 2 because that function is undefined if you try and plug in 2. Number 3 has 2 vertical asymptotes, one at x equals 2, one at x equals -3, because the function is undefined at those points. Okay? Vertical asymptotes also go on your graph as dashed lines. Whoa. Whoa. There we go. Okay. And vertical asymptotes can never, ever, ever, ever be crossed. Okay? You can never cross over a vertical asymptote. We'll learn later on in this chapter that you can cross over a horizontal asymptote, but you can never cross over a vertical asymptote. Might want to write that down. Okay? So, now the big question, question F. Is g of x a function? What are our two tests? Function, not a function. Vertical line test or the tables, right? Okay, you've got them both. Okay? Is g of x a function? Yeah, it's a function. It passes both tests. Okay? It passes both tests. We're done. Oh, describe the domain. So then now, because it's a function, let's describe the domain. So my domain of g of x is going to be all real numbers, but are there any restrictions? Are there any values of x that my function, that I cannot plug into my function? I can't plug in 0. So my domain then is all real numbers, but x cannot equal 0. Okay? Range then is y values. Okay? So you get that off of the graph. So looking at my graph, it's all real numbers with the exception of what's the only value that that function will not get to? 0. It will not get to y equals 0. Okay? The restrictions in the domain, this part right here is the birthplace of your vertical asymptotes. You find the domain first, then that gives you your vertical asymptotes. Okay? This part down here is just a hangout of your horizontal asymptotes. But they're kind of reclusive. Sometimes they show up and sometimes they don't in there because it can cross over and you get that from your graph. Okay? Alright? So, at the bottom of that page 3 then there, that just goes in, and we already talked about vertical asymptotes and horizontal asymptotes, and we already did all that stuff, so I'm not even going to go into that. So, let's go on to page 4. Okay? On page 4 it says, use a graphing calculator to explore various forms of f of x equals a over x, where a is a real number constant. Okay? I've done that for you already. Okay? On all of these graphs, the blue graph is g of x, what you just graphed. Okay? The red graph is what we're dealing with here. Okay? So this f of x here equals 3 over x is the red graph. What's the vertical asymptote of that graph? 0 is just a number. X equals 0 would be a vertical asymptote. All vertical asymptotes are of the form x equals some number. Okay? Looking at the graph and looking at the left and the right sides of my graph, what's the horizontal asymptote of this graph? Y equals 0. The only big difference is bigger outputs, right? Okay? Bigger outputs for red. Okay? Let's go to the next one. Now we've got, this is our red function, negative 1 over x. What's the vertical asymptote? Still x equals 0. What's the horizontal asymptote? Still y equals 0. But what happened to it? We flip-flopped it, right? We either reflected it in the x-axis, or you could say we reflected it in the y-axis. Either way. Okay, next one. Now this is my red. Vertical asymptote. Still x equals 0. Horizontal asymptote. Still y equals 0. Okay. We flip-flopped it, right? We reflected it, and it's got a little bit larger outputs. Okay. Last one. F of x here now is equal to 1 over 2x. Okay. Vertical asymptote. Still x equals 0. Horizontal asymptote. Still y equals 0. Differences. Smaller outputs, right? Yep, that one's just got some smaller outputs. Now, in this chapter, what we're going to be doing is we are going to be manipulating that basic function. You just started with the basic of the basic functions. Now we're going to manipulate 1 over x, and we're going to shift it horizontally. We're going to shift it vertically. We're going to add in factors to it so that you have multiple vertical asymptotes. But you can only have 1 horizontal asymptote at one time. And you can have as many verticals, but only 1 horizontal.